What's up, everyone? This is LeetCode 310, minimum height trees. We've done this problem in Python. It's time for C++. I'm not going to read the problem statement. I don't want to spend too much time on it. You can read it for yourself. Pause the video and do what you need to do. But basically, we're just giving a tree, right? No cycles or anything. And basically, we out of all these nodes, we have to pick the node that's basically that we are going to make our root such that it'll give us the minimum, the tree with the minimum height, right? So in terms of approaching this problem, I'll just get right down to it, right? This is a tricky tree problem. I've watched a few videos on this because I was stuck on it, right? You probably are too, that's why you're here. A lot of these videos aren't really clear on what the solution's clear, but the the way they explain the implementation is not clear. But one thing a lot of these videos had in common anyways, just getting to my point, is that this is kind of a tricky problem. It's more on the harder side of medium, so don't feel too bad. This is a pretty difficult problem. But anyways, in terms of the approach, really the idea is you have some graph, or not some graph, you have some tree basically, right? It's basically a tree. And the way to basically approach this problem, and sorry for these arrows, this should be a line, not an arrow. These are edges, right? The trick to this problem really is you basically want to think of the approach kind of like an onion, right? What do you do with onions? You peel out the outer layer, then the next outer layer, and we're going to basically do the same with this tree by doing that to the leaves, right? And what are leaves? They're basically just nodes which only have one connection, right? Or one edge, right? So here's a leaf, 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 right? So basically the outside part of the tree. Okay, so at every iteration, let's remove the leaves. Okay, so remove this, remove this, remove this. Now we're left with this. So in terms of, we're going to keep doing this, removing the leaves and the leaves. And how do we know when to stop? Basically, when we have two or less, less than or equal to two nodes left, that's when we can stop, right? Because if we have something like this, we can't really remove these without having any nodes left over, right? What would our root even be? It doesn't even make sense. So if you have two nodes left over, basically you would just stop and return both of those because either of these are fine. And to kind of highlight that, we'll go to example 2, which is the best example to show that, right? Because if we do the same process, right? First iteration, let's remove the leaves, right? So we remove this, 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 and we're left with this, right? Now you can see even if we pick the 4, we have the same thing, right? We remove this, 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 and we have a 3 and a 4. So it doesn't matter whether we pick the 3 or the 4. The minimum height will be the same regardless if we pick the 3 or the 4. So that's why you would return both. Okay. So that's kind of the gist of the problem in terms of how you're gonna approach it. Is you're basically just going to remove the leaf nodes step by step until you have less than or equal to 2 nodes left. Okay. So let's get into this. Okay. And if I have some comments or something, we might go back to that picture. But first of all, let's handle an edge case, which is a case where we could have one node left, or we can only have one node, sorry, as an input, right? Because n could be less than or equal to 1, so you could have one node. That is a possibility. So if n is equal to 1, we basically just want to return 0 because the height would be 0, right? Makes sense. Okay. Now, let's first of all build out our adjacency list. And remember, if you haven't done tree problems in a while, adjacency lists are just about basically mapping nodes to each other, basically connecting them via edges. So A should map to B, B should map to A, etc. Right? Just adjacency list of n, right? And we're going to say vector int degree n0. Right, we'll go to this. So, right, the adjacency list, right, we're just mapping A to B and B to A. The degree really is the number of connections a node has. So initially, when we like form AB, for example, these are the degree gets incremented by 1, so it'd be both 1. Then when we go B to C, right, we do the same thing. So increment the degree by 1 and increment this by 1. And it makes sense that the degree of B should be 2, right, because B has 2 connections, right? It can go this way or this way. Then when we add the D, the same thing, right? We add 1, then we add 1, this should be 3 now. And it makes sense because B has 3 connections, right? That's all the degrees are for, in case you don't remember. I didn't, because honestly, I haven't done tree problems in a while. And I feel like tree problems don't come up too often, or graph problems, where you have to actually use adjacency list. I keep saying tree and graph, but really this is both a tree and a graph type problem. So I kind of use it interchangeably. So I hope you don't get too confused or get too annoyed by that. Okay, so let's now actually so we created the adjacency list, but we need to actually map it, right? So we're gonna say auto edge to the edges. Right, we're gonna say int a is equal to edge of 0, int b is gonna be edge of 1, adjacency list for a is gonna be push back b, right? So basically add the edge a, b, right? We're gonna do the same thing for b. Sorry, I'm not in Python, I should use camel case. It's just a good habit. Good habit to use camel case when I'm in C++. So we're going to say adjacency list of b dot push back. Sorry, LeetCode's actually freezing a little bit. Add edge b to a, right? And then the degree of a, increase that by 1. The degree of b, increase that by 1. Okay. And in terms of how we're going to basically handle these leaves, right? Because we have to remove all the outer layers step by step. We've done problems before with trees where we kind of handle it by level by level. What do we do for that, right? Like a BFS approach. What do we do for that? We basically use a queue, right? So we're going to do the same thing. We're going to use a queue, but obviously this tree can be structured in many ways. So, uh, what does a level even mean in this tree, right? It doesn't mean much. Doesn't, like, what does that even mean? So the way we're going to do this for the leaves really is that every step, we're just gonna append the leaves rather than any particular level, right? Because what does a level even mean in the context of this problem? It doesn't mean anything. So for every iteration, we're gonna basically process the leaves. How? By using a queue, right? So that's what we're gonna do. Okay. And we'll get into basically how do you know whether a node is a leaf, etc. Right? And that's kind of the point of the degrees in this stuff, in case you're picking up on it. We're going to say q int leaves, right? And we're going to basically find the leaves and append the queue, right? So we're going to say for int I 0, I is less than n plus plus, right? And we're going to say if the degree of a particular node is equal to 1, then we can just do leaves.push.i. That makes sense, right? Because this right here should be a 3, sorry. I'll update that. If the degree is 1, it means it's a leaf node because it only has one connection. It means it's on the very outer edge of the tree, right? Or the graph, right? So that's how we know whether something's a leaf, if the degree is basically equal to 1. Okay? So that's how we identify the leaves and append it to the queue. Okay? Pretty simple. This code is going to be really long only because I'm putting my brackets on their own lines, but I'm just doing this for the sake of clarity and making it readable. So I hope that's okay with you. Now, int remaining nodes. Okay. Now we need a variable called remaining nodes because that's basically going to let us know when we should stop, because remaining nodes initially is n, right? Because we're processing all the nodes, but we're stripping the leaves every step. And so when remaining nodes is less than or equal to 2, that's basically when we would stop, right? So that's why we need a variable called remaining nodes, right? So we're going to say while remaining nodes, and again, I should use camel case. Sorry, I'm just in a very bad habit of doing that. So I use Python a lot. So while remaining nodes is greater than 2, it means we can actually continue our algorithm, right? The only time we'll exit this while loop is basically when remaining nodes is less than or equal to 2, which means obviously that's when we should stop anyways, right? So when we have nodes to process, what are we going to do? Well, first of all, we will handle the current layer of leaves, right? So we're going to first decrement the remaining nodes variable by leaf count. Okay. So we're basically just going to say int leaf count is equal to leaves dot size, and then we're going to say remaining nodes is equals count, right? Because initially we have n nodes. Like for example, when we're up here, we have 4 nodes initially. Well, at the first iteration, we're going to process these 3 leaves. So 4 minus 3 is equal to 1. So that'll basically mean we only have 1 remaining node. And that's basically, we need to do that just so we know when to stop. Okay, that's all this is about. Now we're going to do the actual, this is the beefy part of algorithm. It's not beefy, but this is basically where a lot of the work happens, which is where we actually peel off the leaves from the tree. Okay, so we're going to say peel, and again, I hope these comments are helpful. I'm just writing it out methodically like this, so you don't get lost by the code. Otherwise, so many of these solutions to this problem, people just kind of write out their code, and I feel like it's kind of confusing. So I'm kind of writing it out because I actually understand this problem. So I'm just writing it out very explicitly so you understand what we're doing at each step. Okay, so we're gonna peel off the outer layer of leaves. Okay, and we're gonna update the degree of the neighbor of the leaves since the leaf is removed. What does that mean? Right, when we remove this leaf, let me use a different color. We'll use green. When we remove this leaf here, we need to update the degree for B here because it only has 2 connections, right? This is obviously, we would actually remove this as well, but I'm just only I'm only focusing on this leaf right now, right? So when we remove this leaf here, we would need to update the degree for the neighbors of the leaf we're removing because again, the leaf is just not part of the tree anymore. So its neighbors should have their degrees properly updated, okay? And additionally, right, if the degree of the neighbor is equals to 1, it's also a leaf now. So append it to the queue. Okay. What does that mean? I mean, you could just use a very simple example, which would be like, let's say we have something like this, like a really weird tree, right? Right. This right here has 2 neighbors, right? This right here has 2 neighbors. Well, if we remove this leaf, let me use a different color. If we remove this leaf, and we remove this leaf, the degree gets updated, right? It was 2, now it's going to get updated to 1. This was 2, now it's going to update it to 1. And that's basically how we know that these are actually leaves that we can process. So we basically say, hey, wait, the degree here is 1 now. So why don't we take this and append it to the queue, right? Why don't we take this and append it to the queue? And so that the next iteration, we're actually going to process these nodes now because they're actually in the queue now, right? That's kind of how we're shrinking our tree over time and basically processing the new leaves at the same time efficiently. Okay, so we're going to say for int I, 0 I is less than the leaf count, I plus plus, right? We're going to say int leaf is leaves dot front. We're going to say leaves dot pop. Okay, and now let's process the neighbors for that particular leaf we just popped. So we're going to say int neighbor. And this is where the adjacency list comes in, right? So we're going to say the adjacency list, that particular leaf, right? We're going to say the degree of the neighbor should get decreased by 1, right? Because that leaf is getting removed. And now we're going to check, okay, if the degree of that neighbor is equals to 1s, it means that neighbor is actually a leaf itself now. So we can actually just add that neighbor to the queue now. Okay, leaves.push. I was going to use pushback, but it's not what you do with queues. Okay. This is just how I write my code, like brackets on their own lines. I hope it's not too messy. I'll highlight it here just so you kind of know, right? This is where the while loop ends. This is just for the outer for loop, inner for loop. Okay. Now, when we exit this while loop, it means we have basically 2 nodes or less left in the queue, right? And because when we're done, right? Like for example, look at example 1. The 1 is the answer, right? When we remove this, remove this, remove this, this only has this has it's gonna have a connection of 1. Technically the connection will be 0 because we remove all this, but at some point it'll have a 1, right? When we remove this, it only has 2 connections. Remove this, it only has 1 connection. So we would actually add this to the queue. When we remove this, we have nothing left over. So regardless of whether we're like, even after remaining nodes is less than or equal to 2, the remaining nodes themselves, meaning our final answer at the very end, they'll actually be in the queue. So we can actually use that to return the answer, right? We don't have to like store it in some like well actually you do have to store it just because it's C++, but I'm just saying, like in Python, for example, you could just return the list of the leaves. In this problem, I think the return actually is a vector of ints, so you can't return the queue itself. But the point I'm making is the answers themselves at the very end of this algorithm, they'll actually be in the queue themselves. So that's where we're going to retrieve them, right? So we don't have to do anything fancy really. At the end of the algorithm, really the remaining nodes that are in the queue is basically going to be where our answer is, whether that's 1 or 2 nodes, right? So we're going to say vector of int is result, right? We're going to say while leaves is not empty, right? While our queue is not empty, we're basically going to add to our results those leaves, right? So we're going to say result push back. We're going to say leaves dot front, and then we need to make sure we actually pop these, right? And then down here we can return the actual results. Okay. Yeah. The code is kind of long just because I put the brackets on their own lines, but I'm just doing that for the sake of clarity. I forgot my colons here. I'm just doing that for the sake of clarity in terms of making my code readable. I hope you can understand why I write my code like this. Just usually how I write C++. I was writing my code kind of fast and talking, so I might have missed use syntax errors here and there, but overall the structure of the code is correct. Oh, I must have missed something. Hold on. What did I miss? What did I miss? We must be stuck somewhere. Oh, right here, sorry. I accidentally had a typo. I was like, I don't think I should have any TLE. And it seems like I'm not appending to my outputs. There's probably something at the end here. Let me see. The degree. Oh yeah, right here. Yeah, sorry. I was just writing my code fast because I was talking while I was typing. Still something. Let me see. Boop boop. Oh, sorry. Right here, I'm setting it equal to -1. I'm so dumb. We're decreasing the degree, not like assigning it to anything. Sorry, it's just typing really fast, and I have some weird errors, and I have to kind of track down where it happened. But my explanation, everything was correct. It's just some weird typos, so don't worry about it. It's nothing major. But I will go back up and scroll down, right? I'll just go through this again. I don't want to make this video too long. But basically, it's just an edge case, right? We're setting up our adjacency list here, right? The connections, the degrees. Here, we're basically finding the leaves and appending it to the queue, right? Remaining nodes, right? This is what we need to basically know when to exit our while loop. And then in here, right, we're basically just counting the leaves, decrementing it from remaining nodes because we're going to process these leaves. Then we actually process the leaves, append the new leaves that are in the tree now to the queue. and basically make sure we update the degree for the neighbor and stuff. And then right here, right, the final answer will be in the queue, so we actually want to remove it from the queue and put it into a vector and return it, okay? So yeah, that's this problem. It's not, I think the solution, when I break it down step by step like that, should make sense. I don't think it's too complicated. It is really hard to figure out on your own, or at least when you're first learning this problem. So I hope I can make this problem a little bit clearer for you, because, man, this problem was a beast to handle at first. But I hope this helped, and I'll see you in the next one. Peace out.